Okay. Any questions before we get started on the lecture of the course? Um, the problem set one has been posted. It includes subject material that will be covered on Monday. So don't panic that the linear system stuff is in the problem set, but it's all going to be covered on Monday. Oh, okay, great. So there's a review lecture also posted, linked to even in the problem set. I think you guys put links. The TAs so far have done an outstanding job of getting everything organized for this course. So it looks like we're in for a good ride. It's a good team. So that's great. And we're trying to get it cleared up. I think it's by October 10th, people are going to make a decision to stay or not. And so that's when we'll know exactly how many seats are open. So if you are still on the wait list, can hang around for another 2 weeks or something like that. We'll keep updating that. And you should have access to Canvas. If you don't, and you're on the wait list, or you're an undergrad and you don't, etc., talk to me or the TA team, and we'll try and get you access to Canvas so you can just keep up. Okay, today we're going to look at image quality and X-ray imaging, the introduction. And so it's mostly X-ray physics. How do you make X-rays? How do they get absorbed by the patient, et cetera? So all of those physics things that we were talking about sort of in a high level the other day. Here. Okay, so image quality, we're going to start with first. And this is basically how do you quantify whether or not an image is good or bad? Or if you have two images, which one is better? So you'd like to have some kind of quantitative metric to describe the image so that you can say which one is better and which one's going to perform more adequately. The types of images you see in medical imaging are quite varied, right? Here's a CT imaging of the head such that the center and window of this is so that you can see all the bony structure in the head. All the soft tissue is basically the same intensity in this display. Here's an MRI picture where there's very good contrast between the gray matter and white matter and the cerebral spinal fluid in the brain. This is a PET image of a brain. And you can see very quickly it has the same basic structure that you see in MRI, but much lower spatial resolution. It's just blurrier. And so we need to quantify all of these things, the contrast, the spatial resolution, blurriness, and such. And so one of the primary things that we're going to deal with in this course is how imaging systems behave when they're imaging a signal that is oscillating in amplitude at a specific frequency. So in imaging, a frequency is a spatial frequency. It's like, what phase of a sine wave am I in as I move along in space? So it will have cycles per meter is what the sine wave will have, right? Or radians per meter in the image. So here's a simple image that is a constant. So it's got one value in the background. There's no change in the signal as a function of position. Here, if we look and say this is going to be the equation or the expression of our image in this plane, well, there will increase this value of B with respect to the baseline such that some component of the amplitude of this image is this sine wave with this particular frequency. And we look up here, if we set the amplitude to 20%, we start to see some slow modulation of that signal, right? If we crank the relative amplitude between the baseline and the sine wave component to 50%, we see this, and at 100%, we see this, okay? So nothing has changed in terms of the spatial frequency between these images, just the amplitude of this sine wave in that image. And what we're going to find out is that we can build any picture we want by adding up sine waves of different frequencies and different amplitudes. And for a two-dimensional image, these sine waves will have a frequency, an amplitude, and they'll have a direction, right? So they can go diagonally, they can go vertically, they can go horizontally, etc. So we have those degrees of freedom to build a two-dimensional function. The interesting thing about characterizing quantitatively what an imaging system does to a signal, right? We can also boil that down to a very basic behavior. And that is, if I put a sine wave signal into my imaging system, so now I have something I've painted on the wall. It could be this modulating sine wave on the wall. I put up my camera or my imaging system, and I take a picture. And then I ask, what is the amplitude that gets transmitted to my final picture through the system that made that picture? And I do this for different, sine waves and figure out the relative amplitudes. So here's my input at a specific frequency, my imaging system, and my output is changed in amplitude by some amount. And we're going to see that that change in amplitude will be proportional to the frequency of this sine wave in all imaging systems, right? So they may pass frequencies equally while the frequencies are low enough, but then as the frequencies get higher and higher, we'll see that the imaging system eventually fails at resolving that frequency, right? And so that's why you do this with sine waves. Is this is the most basic signal that we can do the analysis upon, right? And our images are going to be composed of these signals, summations of these signals, and so we'll see how the behavior goes. Okay. For example, if I have this test pattern that we create, and I have a low frequency set of bars and a higher frequency going to a much higher frequency, so the bars are closer together, so the cycles per meter goes higher as I go from this pattern to this pattern, right? And I look, I take a picture of this pattern, and this is what comes out of my imaging system. So it's smoothed to some amount, right? But if I look at the depth of this trough and the height of this peak, right? That's the relative amplitude that has been passed through the system. So if I put in a sine wave, this isn't a perfect diagram because this is a sine wave. This is not a sine wave. This is a square wave. So, right, it's a slightly different signal. But the principle is I put in something that is oscillating at this frequency, and I look at what comes out. And I get a slight diminishment of the amplitude of that sine wave. If I do the same thing for a sine wave that has twice the frequency and look and see what comes out, I see that the diminishment of the amplitude is slightly higher. So here I had 80% of my original amplitude. Here I have 56% of my original amplitude. In this one, I increase the frequency, same amplitude. Okay, all of these amplitudes are 1. What I see coming out of my system here is the same frequency comes out, but it's been diminished down to 13% of the original amplitude. So as we get higher in frequency, we see the blurring of the fundamental blurring of this imaging system is incapable, say, of imaging a frequency like this. It just spreads it out into an average value. Okay. And that's not really that difficult to understand, right? It's like if I have a camera and I'm taking a picture of patterns on the wall, and those patterns are, say, vertical bars. I just keep taking pictures, and somebody puts the vertical bars closer together. I take another picture. Eventually, those vertical bars get too close to resolve with my camera. I can put them a micron apart, say, an event, and the camera will not be able to resolve them. So it's what is that behavior as you go to that high frequency is what we'll look at as how to characterize an imaging system. And it's pretty simple. If you plot, so here are my spatial frequencies, right? 1 cycle per millimeter, 2 cycles per millimeter, 4 cycles per millimeter. They're going higher. So I plot versus cycles per millimeter, 1, 2, and 4. What is the diminishment of the amplitude of that sine wave? The DC, it just comes in as 1, right? DC means flat, no sort of oscillation. If I look at a sine wave that has this 1 cycle per millimeter, it's down at 83%. At 2, it goes down to 56%. And at 4, it goes down to 13%. I can do that for many, many tests along here and draw this entire curve, okay? And that curve is called the modulation transfer function of that imaging system. Very important concept. And the modulation transfer function tells you how the high frequencies roll off in amplitude when you're trying to image an object. You can't have infinite spatial resolution, like infinite precision on small dots and edges. Eventually, they roll away for any imaging system. This function tells you precisely how your system does that, right? Question. The question is, why does it roll off at high frequencies? Okay, so the answer is a little complex because depending on the imaging system, it will happen for different reasons. So if I have CT, for example, and I have 1,000 detectors in a line, and each detector is 1 millimeter apart, okay? When I put an object in my field of view and I project X-rays through that object, if the X-rays go into the same detector, when two objects get really, really close together till finally the X-rays are hitting the same detector, I can't resolve them anymore. It just it hits that one detector. So that's a fundamental limitation, is my detector geometry. In optics, if I have lenses and everything, I look down and say, oh, why can't I just keep focusing to go down to atomic resolution? The problem is the wavelength of my photon is bigger than the object I'm trying to image. So the thing that I'm using to image was this reflection of light off, reflecting surfaces in the field of view. When those photons wavelength gets on the order of the object, you just can't resolve differences between those anymore. So there's different reasons why the resolution goes down. And, imaging in its history is like, how do I make an imaging system that has higher and higher and higher resolution? So a microscope has been replaced. Who can tell me what the microscope has been replaced with? Optical microscope that was done by Huygens? Who did the optical microscope? It was like in the, I don't know, 16th century, somebody figured out lenses and started looking at cells. Hooke, maybe, I don't know. I should know that, sorry. ChatGPT will know it though, so you don't have to worry. But anyway, so you're making these optical microscopes. You can make better and better and better and better lenses, right? But finally, the physics of the wavelength of light gets to you, and you can't distinguish things. Anybody know how you go to higher resolution?
Have a higher frequency unit.
Higher frequency photon. Okay, so what we could use what?
Yeah, right.
Yeah, gamma ray, X-ray, something like, so you get X-rays, right? So reflecting off stuff, but you probably blast the sample to smithereens doing that. There's another thing that has even higher or smaller wavelength than photons. Electrons, right? So you fire electrons at the object, and you can do a bunch of things. How many electrons pass through the object? How many electrons bounce off the object? And electrons really small, right? So it can bounce off really tiny features. And that's when you see these amazing images of like bug heads and stuff like that are scattering electron microscopy. So you're rid of the photon limitation, and now you've got an electron microscope. Okay. Yeah.
That means that if we increase the wavelength, the penetrative power should increase, right? Because it is not deflected like very.
Yeah. So the question is, what is the penetration of the photons you're using? They're all photons, even X-rays, and in MRI we're using radio waves. They're photons, right? But they have wavelengths of 4 meters, right, or 2 meters or something like that. So
it is not like if we increase the wavelength, that would mean that these rays will be easily deflectable or.
Well, the thing about radio waves is they just pass right on through you, right? Because the wavelength is so big that you're not going to really have I mean, they'll bounce off. Sure, you can reflect radio waves, but most of them will just pass right through you. So, however, the wavelength's so long, if you tried to do reflective imaging with radio frequency, it's not going to work very well, right? How do you do it with MR? We have a wavelength It's literally 4 meters, or at 300, at 3T, it's like 2 meters, something like that's of a photon. That's a 2 meter wavelength. And we're going to image down to millimeters in a person. It's great, right? This is like when I read this, I was an undergrad in physics in '82, I think, and a Scientific American article came out on this thing, and I was reading this going, holy Toledo, that's so good. It's so clever, like how this is done. I'm just gonna leave it there. Okay, you're gonna figure it out. Okay, so for X-rays or any signal that's coming into, so any object signal that's coming in, we can compose it of these sine waves, and we see how sine waves of higher and higher frequencies get diminished. That's the modulation transfer function. It is a very important concept. So if you put an object in your imager, so this is a CT scanner here, it's like about 60 centimeters across the donut. There's basically an X-ray source here and a detector over here. And this is a simulated human torso, you know, how many X-rays get absorbed. And then in there we have a phantom, and you make phantoms into geometric shapes so that you image them and you know the underlying geometric shape. And ask the question, like, what comes out of the scanner? Is it exactly the same as the phantom? And I know exactly what that shape is. So here's a phantom that has holes drilled in it in the machine shop here at UCSD, and that drove this guy crazy because you can't even see the holes down here. They're so small. So you produce an image and you say, well, what is the separation of these holes or the diameter of a hole that I can detect? And eventually the holes get too small, right? So this is what it looks like at, 100 milliamps on my X-ray tube, and you'll understand that in a minute. And now I crank that up to 380, and I get this picture. Okay, so first, this picture is with fewer photons, and then I crank photons up, I get this picture. So you can see now I can start to resolve more things there, and I can measure which ones I can resolve, and that tells me my modulation transfer function under those two conditions, right? And the reason that the spatial resolution gets better when you use more photons is inside the reconstruction algorithm, the vendor doesn't have to average stuff together to make the signal to noise at all rational, right? When we're making this picture in the raw data, there are so few photons, they start averaging things in space on the detectors, and that blurs the picture. And then you get there and it sharpens it up some more. They don't tell you what they're doing actually underneath. They just do that. But okay, so you can make these measurements with a phantom, and exactly the way we saw in that theoretical thing up top of the sine waves, if I look at the signal modulation of these small dots and I just plot it, and you'll do this in the homework on image J, I think. So you just draw that and you see, okay, in the background, looks like I have, you know, maybe 200, and then I come down, it goes to 100, then comes back up, almost not all the way, right? It's been diminished somewhat, and then up and down, up and down, up and down, okay? If I look at what happens with that image that had only 100 milliamps or like a fourth of the photons, now my plot looks like this. I still have the same background, but I really can't resolve what the heck's going on in here anymore. It's all blurred together, right? So so the modulation transfer function is, a way to write down an equation that says, this is the spatial resolution of your system, okay? If you have that equation for that modulation transfer function. We're going to look at a different way of doing it here. Yeah, you have a question?
You said that you said the first image had lesser number of photons and the second one had more number of photons.
Correct.
So I assume that would be an increase in the intensity of the light, I mean the signal used.
Correct.
But you also mentioned that the diminishment reduces with the increase in frequency. So was the frequency changed, or was that just the same?
Okay, so the question is, we got two things changing here. One is the number of photons, changing the basic signal to noise of the background detector. And the other is the spatial frequency of the input. Did I change that? No, I didn't change that. That's fixed by this phantom. So the spatial frequency is represented by the spacing between these, let me do this one, between these circles. As they come closer together, I need higher spatial frequency to resolve that picture, right? So that's a kind of a fixed thing in the background in your phantom. And then you just look down the phantom and say, where does this signal, which is an oscillating signal, turn into just a bar, right? That's an average, right? There's a more precise way of doing it using these separate holes out here, but we won't get into that right now. So here's another concept for spatial resolution in imaging. And that is, if I have my imaging system and I can create an object that is really, really tiny, like an epsilon dot, right? And I put it in the imaging system and I image that dot, like mathematical dot, what does the image look like? It's not going to be a 1 pixel dot, right? I can reconstruct the image such that I see the shape of the picture of that tiny dot, okay? And normally, in many, many imaging systems, if I put my tiny dot here, and in CT, what we do is we take really good Japanese pens and we break the top of the pen and we take the ballpoint out of the top of the pen. It's like 0.2 millimeters in diameter or something. It's usually made of tungsten. And then you can put it in the scanner and it's a tiny dot in the scanner, right? Another way of doing it is if you have a really thin wire and you put the wire in the scanner, because you can get really, really thin diameter, like 500 micron diameter wire. So what we're going to do is we're going to image that dot, and I'll make a picture of that dot, and it will look like this on my imaging, right? It'll look like a Gaussian, like a normal distribution. It has a hump in the middle, and then it fades off as I go away from the object, right? And this is called the point spread function of the imaging system. So what is the picture of a tiny, tiny dot is the point spread function. And in microscopy, Raleigh came up with this criteria that said, look, if I have two dots, I have a tiny dot over here and a tiny dot over here, and I image them, I get two blobs in my picture. They're two sort of Gaussian blobs. As I move the dots closer together, the two big Gaussian blobs will come closer together until finally I cannot resolve that they are two things. It just looks like one blob, right? And so whatever that distance is, that could be considered your spatial resolution, right? It's like how many microns apart do those things have to come together in order to be unable to resolve them as two distinct objects. And I would say a really good toy problem for you guys to do with MATLAB and ChatGPT is just ask ChatGPT to do this experiment. So just create two Gaussians and say, now bring them together step by step. When do they look like one Gaussian? Like, what is the distance? And literally, you'll be able to do this in like 4 sentences, right? And it'll write the MATLAB code, and then you can plot it and see what's going on, right? So here's an example. This is another phantom. Oh, actually, this might be the same phantom. And this is in a very high resolution photon counting CT scanner, actually. And so here's a dot, tiny dot, and this is one of those ballpoint pen things. I thought they were small, but this scanner can actually resolve them, which is pretty great. So we're just going to look at this part of the field of view next. Zoom it up. Here's my ballpoint thing here. Let's zoom in closer. Well, actually, sorry, I'm going to change it to a color background so that you can see more details of the hump. And then we'll zoom that up, and that's what it looks like. Okay, so this is a really small dot. We'll zoom in closer, and it creates this picture, right? So here's the object, here's the picture. And so this picture is the point spread function. Ideally, this dot would be even smaller, right? Such that I would get a picture like this, like my dot is a tiny thing here, and I get that kind of resolution as to what an image of a tiny dot looks like. So, yep.
This point spread function, probably like it will be dependent upon the intensity of the photons that you would be using to get the response for this dot, right?
That's a great question. So the question is, does the point spread function depend on the energy of the photon that you make the picture, right? That's your basic question. The quick answer to that is no, it does not. So if I have a 30 keV photon versus a 120 keV photon, Normally, the spatial resolution of the system isn't changed, right? The spatial resolution of the system is very dependent on the sampling grid, not really on the energy of the photons. Right? That's, if you want to make a higher resolution CT scanner, make more pixels on your detector. But then you run out of photons in each bin eventually, right? You make them smaller and smaller and smaller, you just run out of photons. It does not depend on the wavelength of photons for X-ray imaging. It does for optics. If you're imaging something that's really, really small and you use lenses, then the wavelength comes in. Here, the wavelength of 30 keV photons and 120 keV photons are so much smaller than what we're imaging here. They're basically points, right? Yeah.
Does it depend on the number of photons? Like if we,
Okay, so the question there is, does the resolution depend on the number of photons that you have used to make your picture? This is a two-stage answer. No is the first, because the photon's going to hit a detector, and the resolution is basically dependent on the dimension of the detector, right? So whether it hits the top left corner, the bottom left corner, or whatever, all the photons will go in there. The problem is when you're making a CT image, if you don't get enough photons in each detector, then the manufacturer starts to average things together to make it smoother, because otherwise it's very noisy. And so that averaging makes your effective detector size get bigger and the resolution goes down. So that's a two-stage thing. Okay, so this is a empirical point spread function. You put an object in the scanner, image the object, and that's what comes out. So you measure it, right? And just directly measure it. And you basically do this experiment where you have an object here and you measure this function. You fit that function to a Gaussian, and then normally you say, what is the full width at half maximum of my Gaussian? And that gives you a dimension that's in millimeters or some sensible unit, right? Okay, so that's spatial resolution. That's the two big concepts there: point spread function, modulation transfer function. I don't know, we have to give away the spill the beans here, but as we're going to see later when we do linear systems and stuff, if you look at the point spread function and you're someone who really knows Fourier theory, you go, what would be the Fourier transform of the point spread function, right? It's the modulation transfer function, right? Which is really cool, right? So basically the point spread function, take its FT, you get the modulation transfer function. One's in spatial space, one's in spatial frequency space. Yeah?
Saying that the point spread function somewhat resemble how we would have a function for Nyquist frequency. So at some point when the aliasing starts, it causes a distortion. So that's kind of what I thought was similar to.
Yep.
So in case we increase the sampling, would it then mean that that we would be able to differentiate them for longer?
Yes, 100%. So if you, yep. The sampling, okay, so the question is, a couple of things came up. One was the Nyquist criteria, one was aliasing. When you basically have objects that are higher frequency than your imaging system can image, they will look like they're lower frequency objects because they start combining together. And the final question was, if you have more detectors, i.e. higher spatial frequency of detectors, yes, it's a higher sampling rate, right? And so what we'll do eventually in CT is we'll look at the sampling rate required, right, to make a good picture in 2D. Like how many, for my detector array, how many views are required to make a good sampling? Okay, we'll get there. Yeah.
Firstly, increase this sampling rate, the full width half maximum of the point spread function. The length in millimeters should still stay the same, right? Only the number of pixels in the
Right, right. So basically, so the question is, how does the sampling rate and the full width half max, how do they behave? If I double my sampling rate, roughly speaking, my full width half max is going to cut in half. Okay. So I double it again, cuts in half again. So my point spread function will get thinner, and the full width half max will get less as I increase my sampling rate. Yeah. And that we'll see that you can pick your sampling rate in MR just by how you do the sampling. For us in CT, it's a little more difficult, right? Because we've got a fixed, sampling grid that we're kind of stuck with, right? We can do a couple of tricks, like push the grid half a sampling unit and stuff like that, but we're pretty well stuck with that grid. Okay, so that's spatial resolution. And obviously a scanner that has, if I go back here, sometimes they'll publish this curve. Well, they won't publish the whole curve, but they'll give you, for their detector and everything combined, they'll give you what the MTF at 10% is. And they'll say, oh, look, ours goes all the way out 13% at 4 cycles per millimeter. That's our spatial resolution. That's what they'll claim is their spatial resolution. So you have to, when the manufacturer gives you that number, you'd like to know the shape of this curve basically and what that means being at 10% and stuff like that. But they'll just give you that single number as their spatial resolution. Full width at half max is the thing that I usually think of in spatial resolution because it's very intuitive. It's like, oh, what is the smallest dot that I can really visualize? And it's in millimeters. It makes sense. Our full width at half max for the CT scanner we have is about 1.2 millimeters, right? Yep.
It's kind of similar to like when you go to the eye doctor, they do the lining up.
Absolutely. Absolutely. So they make things closer and closer together. And so the letters like the E, all the things get closer together. So finally it's just like a rectangle that's shaded in. But if you're at the MVA and you need to pass that eye test, you can guess pretty well just by the shapes, right? So like C's and G's and stuff like that will start mixing together. But your probability, if you just guess, your probability goes down pretty good, right? It's like, oh, it's got to be one of 3 things, So I'll just shoot that one. They go, oh, you want to try that again? And you're like, okay, so you get an extra guess. Okay, contrast is like, how different are the amplitudes of the signals in different places in the image? So ideally, if I'm looking for a tumor in someone's liver or a metastatic, say they have a primary tumor somewhere else in their brain or their breast or something, and you look in their liver and say, do you have anything going on in your liver? So you want to have high contrast. You want the signal of those cells to be much different than the signal of the normal liver cells, right? So that when you look across the field of view, you go, this cluster of pixels right here has a much different signal, right? And then for something like this, oftentimes the spatial resolution isn't the biggest issue. It's can you resolve that, oh yeah, that is a definitive signal difference, and I have detected it and it's big enough to make me concerned. Spatial resolution is way down here. Like you're not going to call it if it's 3 pixels. You're not going to do that, right? Certain things like in your coronaries or something, you might start worrying about it, but for Mets in the liver, you're not going to call it. So you have a different problem. That is like, is the signal difference the right signal difference for a tumor? So we need concepts for signal difference. And in CT, one concept you'll see in the textbook is local contrast. And that is if I have a background, which is say my liver, right? And then I have a target, which is like metastatic lesions in the liver, and I know what those are, then the contrast is the fractional change in signal from the background. And we'll see in X-ray counting statistics, fractional change actually is a sensible way to look at contrast. But the other way is just direct measurement of what are my pixel values here? What are my pixel values here? How big is this difference compared to the noise on both of those signals? Okay, and we'll look at that direct contrast. So here you can see, I have great confidence. I have a background. I know there's something there. There's a hole there, and I know there's something there. So it's that contrast is sufficient for me to make a very confident call that something is there. When we look at contrast, it's always in the context of how much contrast is there with respect to the amount of noise on both of those signals. And so noise looks like this. It basically, here's a MR image with, a signal to noise of about 20, something like that. And if we just add random noise, random amplitudes to the pixels in a completely random way, that is spatially random, then the image starts looking like this eventually. Like the noise takes over. The amplitude of the noise overwhelms the amplitude of the signal. So the signal to noise basically is decreasing because the noise is increasing. So where does this noise come from? In MR, the noise is usually mostly from the patient, okay? So you have electronic systems in an MR where you're measuring radio frequency coming out of the patient with an antenna. And inside that antenna will be preamplifiers and things like that, and tuning circuits and whatnot. All of those electronic devices have an internal amount of noise called Johnson thermal noise. If you take a resistor and you put clips across the resistor and you look at a voltmeter and there's nothing across there, you just keep cranking the amplitude, you will see there's a random signal on that resistor, and it's just thermal motions of charged particles in the resistor. If you dip it in, say, liquid nitrogen, the noise goes down because the motion slows down. If you take it, you put it in an oven, the noise goes up because the thermal motion goes up, right? So that thermal motion, can't get rid of that. That's always going to be in your electronics, right? The fascinating thing about magnetic resonance is if you take that antenna and you pull it away from the patient and you make your noise measurement on your scope, right? And remarkably, you're in an RF box enclosure. No RF gets in this room. And so you look at your noise, and now you take that and you put it on the patient, the noise goes like this, right? So the patient is noisy, right? The patient produces random thermal motions of charged particles that give you the noise, and that's the primary source of noise. In CT, the big source of the noise is just the uncertainty in photon counting. So as I get more and more photons, my estimate of the mean number of photons that I just got, at that point in space, that estimate gets more and more accurate, right? As n comes down, my estimate, the relative noise uncertainty in the number goes up and up as n goes down. If n is greater than, say, 20 or so, the statistics are quite simple. The statistics just go as the square root of the number of photons. So your signal to noise goes up as the root of the number of photons, right? When you get down into low photon numbers, the statistics change. They sort of evolve over to Poisson statistics. And so when you're down in the 5, 8 photons, then the noise actually is much higher, right? Relatively speaking. And in radioactive decay, there's obviously uncertainty as to whether or not the particle will be emitted, right, from this nucleus or whatever. Two other things which aren't noise that you have to keep in mind are clutter. And clutter is if the field of view is very complex, there's a lot of stuff going on, the human observer may miss something because there's just too much stuff going on. So if recall back to the introduction when we looked at that mammogram, the one mammogram that was a full projection view, there was a lot going on in the field of view. And so you had to look through all of that complexity to try and find a lesion. So this is like a kid's game called Where's Waldo, where Waldo, the signal to noise of Waldo is very, very high, like super high. That's not a problem. Noise is not a problem. The problem is there's 1,000 other things there, right, that you have to look through to get to Waldo. So the other thing that can happen in imaging is the imaging system itself can produce artifacts. And what an artifact is, it's a very coherent signal that you detect as a signal, and it's not random, it's not noise, right? So in CT, a classic artifact is there's these streaks that go off something that's small and bright, and those streaks aren't noise, right? They're just like, whoa, that's like, where'd those things come from, right? That's not the object. in this telescope, the JWST, like when you look at close stars and you can see down into the background of the point spread function of this telescope, it has these crazy diamond-like structures that go out, right? And you're like, why don't you just get rid of those? I mean, you could filter those out, but they don't. I think it's because it looks different than Hubble, right? Which has a different artifact, and it looks festive. Right? It's just like, oh, look at all these stars. It looks like Christmas all the time. Okay, so anyway, that's the point spread function, an artifact from the fact that they're this shape. In MR, artifacts come in all sorts, shapes and sizes. You can get a flipped mirror image of the whole field of view just superimposed on your picture. You can get repeated structures in the phase encoding direction. If they're moving, for example, if there's some kind of a vessel that's in the field can show up a bunch of times, right, at different offsets. And my theory or my creed by which I live is like one person's artifact is another person's technique. Okay. If you can make, so when you're looking at a picture and say it's an MR picture and all the vessels are doing some strange pattern, you go, huh, how do we encode flow using this signal, right? It's a signal. It's something that you didn't predict, but if you knew how to control it, you could image it, right? And so a lot of artifacts can be turned into good imaging techniques. So, but in MR, there's books, like there's like, you know, review articles of the 94 most prominent artifacts in MRI. Right? So signal to noise ratio, here we'll start with, say, a SNR of 20. In this corner here, we have an SNR of like 0.1 or something like that. You can increase the signal to noise ratio by just smoothing and averaging. Say, take every neighbor that you have, average yourself with those neighbors. And if you're a pixel, and you'll get a signal to noise that is higher, but your spatial resolution is lower. Okay, so there's a trade-off between spatial resolution and signal to noise. So this picture, as we blur it, it just becomes a blurrier picture, but with higher signal to noise. So you have to decide, what's my most important criteria at this moment? Do I need spatial resolution or do I need signal to noise? Yeah.
So is the blurring decreasing the noise? Because you're not adding any more signal to it.
Correct. All the blurring does is because if I'm a pixel sitting here, the pixels around me have random signal on them from the noise process. If I average a group of them together, the amount of noise goes down. But the true dimension of my pixel has gone up. Okay. All right. So here's an example of, again, this is a phantom. We 3D print these phantoms that look like hearts. This is a fluid inside the chamber. This is the material used on the 3D printer. And so this signal should all be identical, right? It's a fluid. It has exactly the same X-ray attenuation as a function of position over here. This is what it looks like when you use 50 MA. So, you know, like a factor of 12 drop from here, and we get sort of uncertainty in the actual value, right? And which shows up as noise. Now, the reason at 50 MA, I can still make a good picture is because this is an object in air. There's nothing around it. So I'm using all of those photons to make this picture. If this was in the middle of somebody's chest, it wouldn't look so good, right? Because the photons would be gone. But you can quantify the signal to noise. So here, if I take a region here of how many pixels, I don't know, but it's this area here is probably like, I don't know, a few hundred pixels. The mean is 675. That's what that says. The standard deviation is 11. So that means the standard deviation around that mean, as I look at all those pixels, is 11. I go over here, mean 672, same mean. Okay, so it's all should be at the same value. Luckily, things don't go up and down as the signal to noise change, but the standard deviation is 30 right here. So it's just a lower signal to noise. Look at these ones. These ones are interesting. Air, here I have a mean of minus 1,000, right? Which is, it's kind of set by the scanner. And the standard deviation is 5. And that's because a ton of photons were used to make that estimate, right? Because all the photons go through air, nothing gets absorbed. Over here, the mean is again minus 1,000, but a standard deviation of 20. So this is what the histogram looks like if you take a set of pixels and I look at the background and say, okay, its mean value is the mean value of this Gaussian distribution of values around the mean. And the width of that, the sigma of that Gaussian is 3.4. In this image, which has lower signal to noise or higher noise, you can see the width of that Gaussian that envelops all of these pixel values is 8.3. Right? So that's how we measure signal to noise quantitatively, right? We say, what's the contrast to noise between this, signal and the background? So I put a profile through here. You can do it in image J. The background is up here around 200, but we know we already measured it at 195. It goes down to 115. So the signal minus the background divided by the noise, which is 3.4, gives us this ratio, minus 23.5. So that's your signal to noise ratio for that object in this background. If I look at the lower signal to noise picture and draw that, I didn't move the object, right? So I can just draw a line in the same place. Here's my minimum now is 156. My maximum is the same. We measured it in the background, 156 minus 1. So that's the difference between the signal and the background divided by the noise level is minus 4.3. 24. So obviously, if you have a signal to noise of 20, you've just learned something. You're always going to be able to see that object, right? Signal noise of 20 is a lot. Yeah. That's correct. If we go back here, it was the standard deviation of this Gaussian that was fit the noise background distribution. And this 8.3 came from this one here. And yeah, great question. So that's the standard deviation there. I should put the formula here so that it's more obvious. I'll do that next year. Okay, so signal to noise of 20, very high confidence in answering the question, is there a black dot there? So this radiology questions come in that form. It's like, is there a black dot here? Or is there a metastatic lesion in this liver? Right? So it's a binary output. It's like, yes, no, right? So it's a very simple thing. Here, we're going to say yes with super confidence. We're going to be right 99.99% of the time, right? Here, is there a black dot there? Is there a lesion there? What am I going to say? I'm going to say, I don't know, right? Because look, if I look at this dot, I know it's there because it's in the same place, right? But look at all these things over here. They're equally valid dots compared to that, right? So the signal to noise of 4 is way below my threshold for saying, yeah, that's a positive signal, right? And it turns out there's this thing called the Rose criterion, where if you have a signal to noise of 5, that's the threshold for a machine to operate at and get about 95% of the calls right? Humans will not operate there usually. If you present a radiologist consistent pictures that have a signal to noise of 5 and you say, you have to make your call based on that, they will throw that back at you and say, buy another machine. What is this thing, right? So they don't like working at a signal to noise of 5. They like working at like 10 or something like that. So however, machines will work at wherever you program to work, right? Radiologists work at their own thresholds. They have different thresholds. So it's hard to keep up. Okay, any questions about signal to noise, contrast to noise, amplitude, anything like that? Okay, yeah.
So a lesser contrast to noise ratio means that your picture is of higher resolution. It seems like
Well, is that you don't want to make such a generalization as that. However, you're on the right track in that I can reduce my signal to noise, or let's do it the other way around. If I have high resolution picture, right, and I want to increase my signal to noise, I can do so by averaging pixels together, smoothing the picture. However, at that point, I have cut off my ability to detect some high resolution objects. But if my object that I'm trying to detect is like a big thing, it's a disk that's like 2 centimeters in diameter, that's what I really want to detect, then it makes sense, right? To actually smooth your picture such that your signal to noise gets much higher. That's a good question. Yeah. Oh, sure. Is it, did I not put it anywhere? Maybe I didn't. Okay, sorry about that. So the contrast to noise is the signal of your target minus the signal of the background divided by the standard deviation, in this case, of the background. Standard deviation of the background, because that's what we measured, right? When we came out here, this is the standard deviation of the background, standard deviation of the background. That should be somewhere. I don't know. Okay, well, sorry about that. I'll put that in next year. Okay. That's spatial resolution, signal to noise, contrast to noise, stuff like that. We're gonna now change gears entirely and look at how X-rays are made and then how X-rays interact with matter to produce contrast. Okay. So this is like X-ray physics, essentially. So here's an image of a hand taken with a plain film X-ray, and you can see the very beautiful high resolution details of structure in the bone and things like that. This is actually a negative of what is detected because the bright stuff here actually absorbed more photons than the dark stuff. Okay, so they flipped the contrast, they've inverted the contrast. And the reason you invert the contrast is that it looks like the object itself is illuminating the space as opposed to being a shadow. So people are somewhat more comfortable looking at something and saying, oh, it's illuminating something as opposed to it's causing a shadow. Yeah.
When they did this on film, did it come out looking like this on the actual negative film, or did it come out looking the opposite because it's being hit with?
No, it comes out looking like this because you basically have more flashes where the X-rays are,
Right.
right?
So it's like optical film in the visible
Right.
spectrum, basically.
Right. So whenever you see somebody reading X-ray film, it's in this orientation, right? So here's how the geometry of how that's done. We've got an X-ray tube up here producing an X-ray beam. Patient is between the source of that beam and the detector, which slides in. It's usually either a digital device that you can move around, or in the old days, it was a cassette, which was a film screen system. And X-rays, so here, we talked about this in the introduction. Here's the electromagnetic spectrum in terms of the wavelength of the photon, or the plane wave, however you want to think about it. In X-rays, you usually think of a photon. In RF, you usually think of a plane wave. And this is the energy of a photon at that wavelength. And so when we're up at X-rays in the spectrum, above ultraviolet, below gamma rays, that usually you talk about the photons in terms of their energy, the energy that each photon packs, right? As it is flying through space, hits a target, that's how much energy it has to deliver to the target, right? And in order to have that much energy, it must have gone through a process that created that much energy in that photon, yeah? Oh, up here, it's still a photon, it just has much higher energy. Say again? Oh, no. I'm sorry, the photon. That's a great question because I wondered why they put this here. That is a nuclear power plant. This is like, I grew up in the age where we had nuclear power plants all around. This probably is not 3 Mile Island. They probably picked a different one, but it's a cooling tower, yeah. But somewhere down in here, they're, turning basically neutrons are the things that are wailing around in that thing, not so much gamma rays, but lots of radiations coming out of there. Yeah.
Energy depends on both
magnitude and the frequency of the wavelength. So if we are saying that if we increase the frequency, the energy increases, but like are we assuming that the magnitude of the wave stays same?
That's a really great question, and that goes back to fundamental physics. And Albert Einstein, he didn't win the Nobel Prize for general relativity. He won the Nobel Prize for the photoelectric effect, which is fascinating in that the amplitude of a photon really doesn't change. What changes is its frequency, and the energy that that photon packs is proportional to Planck's constant, h nu, the frequency of the photon. Well, that's it. You can't like crank the amplitude of a photon at that frequency. It just flies at the speed of light, and when it hits something, that's how much energy it has. It's h nu. That's it.
Does that mean that the magnitude depends on the mass of it, or is that also not?
It has no mass, which is fascinating in its own right, right? It's something that has different amounts of energy, and it's a massless particle that flies at the speed of light.
All the electromagnetic radiation that we have will always have the exact same amplitude.
Well, yes, if you look at it as photons. However, by the time we get to MR, we're down here. We're way down here, right? So this is between 30 and 300 megahertz is the frequency of that. And looking at photons at 300 megahertz is not very practical. Nobody does it. Everybody thinks about it in terms of a plane wave, of electromagnetic plane wave. And that's how you model that. And that's like a macroscopic model of what's going on in your antenna or your receiver or anything like that. You think of it as a plane wave of electric fields oscillating, magnetic fields oscillating, and hitting your antenna. It would be fascinating if anyone wants to do this as a project, explain MRI and say the Bloch equations in terms of fundamental photon physics, not E&M, but fundamental quantum mechanics. Like what's going on there? When I irradiate the sample and then I get RF coming out of the sample, that's photons, right, coming out of the sample. They're these big, long wavelength photons. But like, how does that work? Yeah.
So if photons don't change their amplitude, going back to the first slide today, what is changing? What wave is changing in amplitude then after going through the sample? If it's not the photons.
Oh, it's just the number. So it's the number of photons changes. Okay, so the different intensity I get in my image is just counting photons. It's the number. So when you're saying, okay, let me just go forward with that. So the question is, it's an interesting question. So when we go back to that sine wave thing, it's like that looked like a sine wave. Isn't that a photon? That's not a photon. What that sine wave is, let's go back and make sure we get this right. Here. What this represents is the number of photons that are being absorbed as a function of position in space. Okay, so this would mean a lot of photons are getting absorbed at this location, and this is not that many are getting absorbed at this location. A lot of photons are getting absorbed, not as many. So basically, it's just a pattern of intensities of, in the case of what we're doing is I put up an object and it casts a shadow. And this is the shape of that shadow. And so at this point, all we're doing is the photons are just particles that we're counting. Okay. The energy of those particles can be different. And those particles, photon particles, as their energy changes, their behavior in terms of ability to pass through material changes. Okay. But let's not confuse the frequency of the photon with the frequency of the imaging system. They're in two different domains, right? Completely different. Right?
Thank you.
Sure.
So just to summarize, like the magnitude of electromagnetic particles is constant only as the frequency is like very high, but if you see like lower frequency objects like, so like lower frequency waves like my, microwaves, we can have like different frequencies if you view them as a wave, instead of seeing them as a particle.
Correct. So the question is, like, at a certain point, it no longer is to your advantage to model RF or, EM radiation as a particle. Where we're operating in X-ray imaging, it makes sense to look at it as a particle, as each photon, right? As just bing, that's something that shot through, and that object either deflected off my thing or it didn't, right? So they're collisions of particles as opposed to a wave that you would model. Okay. And I realize we've got a lot of frequencies running around here. The fundamental thing in imaging is the spatial frequency. Okay, so it's the cycles per millimeter of the pattern of the thing I'm imaging. The frequency we're talking about here in this megahertz is the frequency of the radio frequency energy that's coming through. That has nothing to do with the spatial frequency of my picture. Okay. But Fourier comes into life everywhere. And so you basically think of these frequencies and they're, basically the spatial frequency and space and temporal frequency, right? And frequency, So, okay, so let's, so this is an X-ray tube. This is a tiny little one. This isn't a very sophisticated one, but it's a really nice picture. It has a motor here, and that motor is going to spin this disc, and this disc spins so that it doesn't heat up when electrons burn off this cathode and hit this disc. Okay, so that's the geometry of how things are going to go. This is charge negative. This is charge positive. You crank a voltage up between these two, which is very high, say 100 kilovolts between those two surfaces. And then the X-rays are going to fly across here and hit this target. 98% of the energy of those collisions of the electrons onto the target get turned into heat, right? 2% or so generate X-rays that come flying out of this tube. So it's an X-ray light bulb, okay? And this is what, a real one that you would find in a scanner looks like. So you've got this big motor here that is going to spin that anode that we just saw, and this spinning is very high frequency. It's like 10,000 RPM or something. And then this is our cathode, and there's a wire current comes in here across the cathode filament, and electrons come across here. And this is the drawing of that assembly. This all happens at a vacuum, so the electrons don't ionize gas and all that kind of stuff. The electrons are going to fire across here at, because of these voltages. And that's why the energy is of the X-ray we're going to get is in electron volts, right? It just comes directly from this. We set the voltage here. Let's say we set it to 140 kilovolts. If all of the energy of 140 kilovolt acceleration of this electron goes in there, you get 140 kilowatt photon coming out, or KeV photon, kilo electron volts. So what else do we need to say here? So this cathode is usually made of something, you heat it up very high and electrons just like bubble off of it, boil off of it. This is rotating very fast, and this hits, ideally it would hit, if you want the highest resolution imaging system you can, you want your source to be a point, right? So all the X-rays come out from a point. However, that's impossible because you would fry that point. So they usually make it a rectangle, just so they don't burn this thing up. Okay, I think that's it. We can change the amount of tube current across this cathode. And remember when I said that high resolution picture had 300 MA and the lower one had 50 MA, that's the current that's going through here. So that just means more or fewer electrons go through, right? So if I double the tube current, the number of photons coming out doubles. Yeah.
So what 2%, or was that way back when first X-ray tube?
Say that again, I'm sorry.
The 2% you said electrons hitting the anode and only 2% of it actually produce X-rays?
Right.
Is that still the case?
Still the case. Yeah, still the case. Most of it just goes into thermal energy. So here's what happens when the electrons go into the target. Okay, so here's the electron flying into the target. It hits an electron in some atom, right, and knocks it out as a very speedy electron. And the original electron gets deflected in this direction, and a new electron gets deflected in that direction. So now I have two electrons flying through this stuff, right? And then that one hits again, and one comes out, and this one can come, and you get a shower of electrons that just go, and then all of that gets absorbed as heat energy, right? Just sort of kinetic energy put into the system. So this is what mostly happens. This doesn't help us at all other than heating up the target. This is the stuff that makes the photons that we want. The first is a very particular interaction in which the electron comes through and it hits an electron in one of the inner orbits of a molecule or an atom, and it will eject that electron. It just knocks it out of that orbit. So it goes off with certain momentum and energy, right? And then an outer shell electron from that atom will drop in to fill that space immediately. And when it does that drop, it emits a photon, and that's called a characteristic X-ray. That X-ray comes out at a very particular energy, which is the difference in energy between this orbital and this orbital, right? So it just goes bloop, and then the X-ray comes out, and it's got a characteristic energy. And so you can tell what a material is by looking at some of these energies. Yeah. That's, yeah.
Decide the frequency of the related on the number of photons.
Number. Okay, so the current will decide the number of photons, and the voltage will decide the energy spectrum of the photons. So if I crank the voltage up, I can get higher energy photons because I have higher energy electrons coming across. We can go back and look at the drawing. So here's my electrons coming across. Let's say I set this to 100 kilovolts between here and here. They accelerate to a certain velocity by the time they hit the target, and that's set by the 100 kilovolts. And you'll do this in the problem set. It's not a small velocity. By the time they get across there, they are really flying, okay? And I won't give you the answer because when you do it, you go, that can't be right, and you do it again. Yeah. So they fly across there, and that sets the energy, the maximum energy possible for a photon coming out of here. Okay, if all of that energy got turned into one photon. Okay, if I want twice as many photons, I can change the current here by a factor of 2, put it up, and I'll get twice as many photons with the same energy spectrum, right? And if I want energies at a higher photons with higher energy, shorter wavelength, I turn up the voltage, and then I have higher energy photons. Yeah.
If the characteristic X-ray is coming off of the inner shell, does the quantity of X-rays produced depend on the material that you use to construct the anode?
Yes.
So is that why they use different materials for different applications?
I think so. That's a good question. Like it's mostly molybdenum and something else, tungsten or something.
These are pretty up there.
Yeah. So they're big molecules. You want a lot of electrons, so a lot of potential for this kind of absorption. However, the characteristic X-rays make up a small fraction of the total spectrum of X-rays that come out, because most of the X-rays that are produced by this process, which is called Bremsstrahlung or breaking radiation. It's German. And what happens is the electron flies by a nucleus and it gets close enough to the nucleus to interact with it in some way, some quantum mechanical way, such that that collision, right? It doesn't have to hit it. It just gets close into its orbit such that some quantum mechanical way it says, "Oh, I've changed my energy and momentum to go this way," and it produces a photon, right, from that radiation. And so, if this is a glancing blow, this photon will be of low energy. If it's a direct hit, if the electron goes whoop and like gets popped right back, all of the energy goes into the photon and it becomes that high energy photon, that 140 keV photon or whatever. But the vast majority of photons that are created this way are from these glancing blows, because the cross-sectional probability of one of those is so much higher than hitting the nucleus right on. So that's what you get, is most of it comes out like this. And you get more and more lower energy photons as time goes on. But the low energy ones, actually, they're absorbed so readily, like by matter, that they don't even make it out of the target. So they're produced in the target, and that lower energy X-ray comes out, and a lot of them don't even come out of the target because they interact with the target, and then they have to get through the glass, and then they usually have to get through a filter. So here's what the spectrum of X-rays looks like from this Bremsstrahlung radiation. So if we set our kilovolts to 100 kilovolts, the highest energy photon I can get is going to be up here. I don't get that many of those because I have to have a direct hit, right, on the nucleus to get that. But as the energy goes down and the probability of that type of interaction goes up, I get more and more photons at that energy. So if I set to 100 keV, I get photons at all of these energies. And this is the relative number. So it's like the probability density function for photons at that energy. Yeah, there's a question at the back.
The should have like red marks too, or the difference between like fluorescence that you get.
Does it have what? I missed the first noun. Does it have what?
Is like the radiative transfer, is that the same like type of energy transfer that happens in FRET?
Oh, fret. Oh, that's fluorescence. That's remind me what fret does. I forget. I'll look that up, or I'll type it into ChatGPT and give you an answer next time. Okay. Okay. I forget how you do energy transfer in fret, but anyway. I doubt it. It's yeah. Because this is like high energy physics, right? This is like I'm shooting electrons. So I've got an electron collider and I'm shooting it into my target. And depending on how the electron interacts with the nucleus, which is the target, pushes off these photons, right? A lot of other things can happen. Okay, so notice, this is important, the X-rays drop to almost zero down at these low energies. And that's because they get absorbed by the target or absorbed by the glass, or we're going to put a piece of copper or aluminum just outside the X-ray tube. So if I'll put right here in my object, I'll put, say, a thin piece of copper, and it will take out all the low energy X-rays. It will let the high energy X-rays pass through, but the lower energy X-rays, it'll just take them out. They'll absorb there. The reason you want to do that is you don't want to shoot those lower energy X-rays into the patient, because all they do is give you more dose. They have no chance of getting through the patient. So you don't want to irradiate the patient with those. You want to irradiate them with photons that have a chance of getting through, right? Yeah. What's the direction? They go in all directions. If I hit my target here, I'm basically going to get through a sphere of X-rays is going to come out. Okay, all directions. And we just conically aim them with you know, sepia and stuff like that to make a beam come out. And you just absorb all the rest. Okay. Okay. Where are we? I got 5 minutes. 5 minutes. Okay. Okay. So this can be a confusing part because now we're going to do X-ray interaction with matter. The drawings look very similar to what we just did. Okay. But there's a distinct line here. What we just looked at was electrons hitting a target to produce X-rays. Okay. And so that's a collision experiment, you know, like anything. So those are electrons from my cathode hitting my anode, making X-rays. Now these are going to be photons. These are the X-rays. And this stuff here is inside the patient or your target. Okay, so these atoms are the things inside. So now the photon's going to go and try and pass through the patient. Okay, and then a lot of things can happen, but 3 major things you need to understand. One is that the incident photon can basically knock out an electron that's in an orbit. Another electron can drop into that orbit that just got knocked out, and you get characteristic radiation, which is again a photon coming out due to that dropping. So that's exactly what we saw with characteristic, right? X-rays with the electrons, okay, when they knocked something out of a lower energy orbit. So that can happen, but now the incident particle is the X-ray photon, okay? It doesn't necessarily, when this happens, when the incident photon or incident X-ray knocks a photoelectron out, when that drop happens, right, the energy that can come out of that system can also be an electron, right? It'll just eject an electron. And that's called an Auger electron instead of a photon. An electron comes out of the atom. So it's another electron. This electron comes out with fairly low energy, so it gets absorbed immediately, like within picometers, it just gets absorbed, right? So those are 2 methods for what is called the photoelectric effect, and that is when you've completely absorbed the X-ray when it hits the atom and it knocks one of these electrons out. Okay, so that's photoelectric effect. Notice the X-ray stopped in both those cases. It just ended its journey right there. Another thing can happen is that an incident photon can basically interact with an electron, but not knock it out. It just interacts with it such that, well, actually, I'm sorry. It knocks it out, but it itself, the incident photon comes off, right, with a changed momentum and a changed energy. So here I am, I'm a X-ray photon, I'm flying through, I have a specific energy. I hit an electron at a certain interaction angle in an atom. That electron goes off, and I don't disappear. I actually go off to preserve the, like, momentum has to be preserved and energy has to be preserved. I go off in a different direction. So my energy has to have dropped, and my direction, it balances the momentum of that collision. And so now I have this Compton photon, which was my original X-ray modified by that collision, okay? This also is a good way to eliminate photons on their pathway through a patient, because if this angle is high enough, when that photon comes down to my target, it will be coming at a specific angle such that I can filter it out just with a sepia grid, with an anti-scatter grid. So this type of interaction, by the time we get to photons of energy in the 100 keV, this type of interaction produces 99% of the reduction in incident photons. We'll see the relative amounts, but there's basically the photoelectric effect where the photon goes away and the Compton scattering. Okay, now looking at a complication down the line, if this angle isn't high enough, it can be just deviated just a little bit, it produces what's called scatter. And so it gives an erroneous signal in your detector because you detected at a certain detector position that you assumed came through the patient on one trajectory, but it actually came through on another trajectory. So that produces what's called scatter, which is a sort of a random signals in the background. Okay, we'll start here on Wednesday, looking at the relative probabilities of those two types of interaction, the photoelectric and the Compton scattering. And I'll be around for any questions.
Alright, what is better? Right, if I go on.